My name is Rúnar, and I want to talk to you about Unison. Okay, so first, who am I? I am co-founder of a company named Unison Computing, which is a public benefit corporation based in Boston. I'm also an author of this book, Functional Programming in Scala, which is affectionately known as the Red Book. And my agenda here today is to tell you about Unison, which is this awesome programming language that I'm working on along with my coworkers at Unison Computing. And I want to show you some Unison code. And mostly, I think I want to just answer your questions about it and just sort of have a conversation. Okay, so great. Let's get into it. What actually is Unison? So Unison is a strongly statically typed, purely functional programming language. It's a general purpose language. It is strictly evaluated just like Scala. It looks a lot like Haskell in the syntax, but as we'll maybe or maybe not get into, that's only a surface similarity, and the surface syntax can, at least in principle, be completely resurfaced. Like we have ideas for adding like a Lisp-like syntax and maybe something that looks like Python, and that's completely sort of pluggable. Okay, it's open source under an MIT license, so anyone can contribute, and we have an active community of friendly contributors. It's similar, again to Haskell, similar to Smalltalk in a lot of ways, which we'll get into, but it's actually totally new and different from any of these. Okay, so why are we making a new programming language? So humanity has been programming in high-level languages for about 60 years now, which is not a long time. But along the way, we've experimented with various language designs. But sort of in the core ideas, most languages in use today are not significantly different from ALGOL 68 or Fortran, or they actually are Fortran. So also the thing is that the programming language that we're programming in is actually only one aspect of the overall software development experience today. And we have all of these other things or activities that we engage in as software developers that aren't programming, like version control, using Git and GitHub, collaborating with other people, doing builds and continuous integration, there's Circle CI and Travis, and there's deployment and distribution, cloud infrastructure and DevOps and ops, and all of this stuff, CloudFormation templates and Kubernetes and whatnot. And none of that stuff is actually in the programming language, which is something that we want to change. So almost none of that extra stuff is intentionally designed for the programming experience. It's sort of tacked on in an ad hoc, pragmatic way, and sort of incrementally building on what came before. And, we still use old-fashioned text editors to mutate bags of text files on disk that we share around with tools that don't understand anything of the actual code and the way that it's structured. And, I like to say that modern systems just sort of hang together with op stuff and Unix. And when you really start looking into like how systems hang together, it's terrifying. Okay, so the thing that we want to sort of ask ourselves is, what would a 21st century developer experience look like? Like if you could just sort of revisit all of the assumptions of the developer experience, what would we change, and what lessons from software development from the past 60 years would we apply to our design? And so Unison is our answer to this question, or at least sort of an attempt to start to answer this question. So we wanted to revisit everything about the software development experience, starting from the very basics of how a language is structured. Okay, so Unison is in alpha. And again, the Unison as it exists today is not even close to Unison, the ideal, but it's just sort of gives us a glimpse of what it could be and ought to be. Like there's no graphical IDE. There's, the ergonomics of it are kind of janky at the moment. There are lots of bugs. There are not a lot of libraries available yet. The community is not very big, but it is growing, and we're very friendly. So the impression that I want to make on you today is that Unison has the potential to be completely amazing, and that you can participate in the future today. That you can start programming in Unison now, and there's no setup like that. You don't have to, make a SBT project or download some kind of IDE or anything. You just like install Unison, which is you can install it with like Homebrew or Stack, and you can just go to town. As we'll see, the friction for getting started is very, very low. Okay. The big ideas behind Unison are basically two, but they're sort of intimately connected. First of all, Unison code is not text. It's structured, immutable data. And so a code base in Unison is a database. And secondly, every Unison definition, both types and functions and values in the code base, they're all referenced by hash and not by name. So in a normal programming language, you'll have something like, collections.list.something, which is a sort of a name that references some code. But depending on when or like what version of stuff you have or whatever, that name can mean different things. But in Unison, every expression has a unique and deterministic global address. And that address is a hash of its implementation. So it never changes. And that has a sort of a profound implication on the design of the rest of the language, which we'll get into. So what this means is that code is sort of content addressed. Like for example, if you've looked into distributed hash tables or what is it called, IPFS, you might be familiar with this idea of content addressed things. So for example, here we have two functions, have and split, and their implementations are very similar. In fact, they're identical except for all of the names, like what we've called the local variables, what we've called the actual function and the argument, and things like that. So this is sort of similar to the Haskell syntax. You'll have, so the first function is named have, and it takes an argument called list, and then it starts a code block, and there's a local variable called n, which is defined to be the size of the list divided by 2, and then it returns a pair, which is n elements from the list, and then all the elements after that. So takes n elements from the list and drops n elements from the list. Okay. And split does the same thing. But so in Unison, these are not two functions. They are in fact the same function in a very precise sense. So every definition has a hash, and so this function have or split is actually called hash A2K14 or something. It has a 512-bit SHA-3 hash, which is its actual Unison name. And the names have and split are just sort of metadata that we attach to these. So you can call them whatever you want. You can rename them at will, etc. Okay. And in fact, everything is referenced by hash. And so all of the things that we're referencing in the definitions of have and split, like take and size, those things are also just hashes. Like they get translated by the compiler to hashes, and then they get actually just replaced. Like before we when you actually generate the code that we put into the code base, we replace the names with hashes. Okay, so this is the sort of the actual structure of the code. Everything just contains hashes. So what this means is that a Unison code base is not a mutable collection of text files. It's an immutable database that stores your code in a computable form. And then all kinds of metadata is attached, like documentation and tests. And the code base actually knows the type and the whole dependency graph of every function, and it knows how your code has evolved over time as well. And so the code base is this database that you can query and manipulate and restructure at will without breaking anyone's code. All right. So, for example, so this is sort of a screenshot from the Unison Codebase Manager. So there's a little program that you run, it's called the UCM, or the Unison Codebase Manager. And you run this, and at the moment, it's just a command line interface, but we're working on a more graphical version of this. And so what you do is, you can manipulate your code base using this tool. So for example, you can ask for the definition of a given function. So here I'm asking for the definition of list.filter, which is in the library called base, or in the namespace called base. So I'm in base, and I say view list.filter, and it gives me the definition of filter. Now, this source code is not in the code base. This source code is actually generated from the compiled form, from the abstract syntax tree, which we actually store in the code base. And just to sort of tell you about this syntax, I'm not sure why I can't get a cursor on this thing. Anyway, well, to tell you about the syntax, so the first line of this is type signature. So list.filter has the type, so colon tells you what the, everything after the colon is the type. So it takes a function from A to Boolean, which may have some effect E. So Unison has an effect system, and that's shown here. We'll talk about that more later. And so it takes a function from A to Boolean, and it takes a list full of A's, and it gives you a list of A's with all of the objects removed that don't match the filter. All right, so we're calling fold left on the list, and for every element we say if the predicate is true for the element, then we add it to the accumulator, or to the list that we return. Otherwise, we drop it. Okay. And documentation is also written in Unison. So you, instead of having like Scala doc or something like that that you do in some other language than your programming language, you usually just write documentation in Unison. So and documentation, you can ask for you can ask the codebase manager for a documentation of a given function if it's defined, and it manages the links between the definitions and the documentation. So here's the documentation for list.filter. And the thing to note here is that the examples are not text; they are actually code, and Unison is evaluating these expressions on the fly, or getting them from a cache if I've evaluated them already. So you know, that's pretty cool. But we'll see that a little bit later. So you actually just construct these Unison expressions and save them as documentation. Okay, yeah, we can ask for all kinds of properties from the codebase manager. Like we can ask, well, like what are the dependencies of a given definition? And we can ask for what are the dependents, like usages. No, wait, dependencies is the usages. No, the other way around. We can ask for what are the usages of a given definition. And so the Unison codebase manager knows all of the structure of the code. I'll stop here for questions if there are any.
Please just jump in if you have questions, but let's kind of see if we can do it.
Is this a JVM language?
No, this is a native language. It's it runs on our runtime so the Unison runtime is native, but this actually compiles to an intermediate language that runs on our runtime. So a sort of bytecode. It compiles the Unison bytecode, basically.
So there's a question in the chat from Jeff Knopf says, what is the database and is it fast?
At the moment, the database is a bunch of files, and it is not fast, like at all. But we're refactoring that right now. And the database that we're using next is SQLite, and that is much, much faster.
So I have one. If the code manager knows, it makes sense that it would know all the things that say list.filter depends upon.
Mm-hmm.
But you said it also knows everything within the code base that depends on list.filter, that uses
Yes.
list.filter, right?
Right.
It seems that would have some implications for packaged third-party libraries.
How so?
Well, so when you say that this is your code base then that we're talking about, so it's the code manager, it's everything within the project that you're building.
Well, in practice, it ends up being just all the code that you've ever worked on or used. Like, you know, we toyed with the idea of having like multiple code bases and stuff like that. But in practice, what you end up wanting to do is just to partition your code base into projects. So you'll just have like one, it's kind of like Smalltalk where you have like one image, which is like all the code that you want to use or that you've written, and it's all in your image. And, you know, when you get other people's code, you just sort of import it into your image.
So does that mean image is project? I realize I'm being kind of brain damaged and stupid here, but.
No, like, you know, you'll organize your projects into namespaces. So like, you know, your Unison code base is really sort of like the root of your hard drive. And you might have lots of different projects you're working on your computer, but, you know, you'll put them in just different directories. And that's kind of how you will work in Unison as well.
So as somebody said in the chat, then all your coding mistakes live forever.
Yes. I mean, at the moment, it's not really possible to delete hashes, but you can hide them. Like you can delete the names and the history and all that stuff, but they'll still be there if somebody wants to go looking. But you know, in principle, there's no reason you couldn't delete hashes that nobody depends upon.
And so one of the other questions then in the chat is that this then is a mono repo by default?
Oh, absolutely. Yeah, it's like the mother of all mono repos. But you know, we'll get to how that, I mean, you can like sort of split things into different, like you can publish things to GitHub into different repos and split things up if you want. So we'll maybe get into that later.
How do you collaborate with other people working on this code?
Well, at the moment you collaborate through sort of this UCM tool. So you collaborate through the codebase manager via GitHub. So you actually just push your code to GitHub in binary form, and then UCM will retrieve it again. And now we realize that's sort of janky, but that's how it works right now in the alpha. But we're hoping that once we get to beta, you know, we'll have a tool that's more similar to GitHub. for collaboration.
Okay.
So,
Any other questions before Rúnar continues?
yeah, so I guess this is probably more of a good problem to have down the road, but the way that everything's in one repo shared, I guess, has interesting implications for software licensing, right?
Yes, and in fact, software licensing is sort of directly supported by UCM, and it's very granular. So different functions in your library can have different licenses, and that's all well supported. So we can maybe get into that later. All right, so we'll get into a bunch of stuff. So what I want to get into is right now is that names don't matter in Unison. So you can think of all Unison types and functions as occupying a vast read-only store, and you sort of like discover them. And every version of everything has a unique and immutable address in this vast store. And that address is the hash of its definition. And a hash can have as many human readable names as you want. And renaming is a trivial non-breaking operation. And reassigning names is also trivial and non-breaking. So in a traditional programming language, everything is referenced by name. I don't know, Scala.lang. something. And that the meaning of that name changes depending on like where you are in space and time. And if the name gets a new definition, which happens, dependencies will break. Like if you were using that name and now it means something else. And if a definition gets a new name, like you were using some definition and now it has moved, if you depend on that name, it's going to break because now the compiler doesn't know what that name means. In Unison, definitions are always referenced by hash, and if a name gets a new definition, it's fine because the hash is the same. And if a definition gets a new name, nothing breaks either. And it's not just like, oh, well, you can trivially rename stuff. No, you can like move stuff around. Like you can move it, like whatever package structure you have right now, you can just change it tomorrow and nobody will notice. I mean, they'll notice once they like look at the source code or whatever, but their code will still work using the new locations of everything in the namespace. Okay, so what hashes allow us to do then is to unambiguously communicate code across time and space. So a given hash always refers to a specific Unison object over memory boundaries and across revisions, across networks, whether it's on disk or in memory or on the network. All right, there are no builds in Unison either. So in a traditional language, you might have a build, so the purpose of a build is really to ensure that all the code in your project can address the other code that your project is using, whether that's on memory or on disk. And so it makes sure that the names refer to versions that you are actually wanting to use and are actually able to use logically. So it makes sure that everything type checks and all the tests run. And it does this every time you run your build, right? But in Unison, definitions are referenced by hash in this global eternal address space. And a hash is always the correct version. There's no ambiguity about what that is. And so you never need to rebuild anything. And a given hash really only needs to be compiled once. And also, if you have tests on that hash, those tests also only need to be run once, as long as they don't have any side effects. We also don't have dependency conflicts, like not really. So in a traditional programming language, dependencies are these sort of build artifacts. So they're things that are generated by builds. And they're usually referenced by like the language version and the package version. And those names can be sort of taken, like different versions of things can't coexist. You can't have like the Scala 3 version of a library and the Scala 2 version of a library sort of coexisting, or like two different versions of FS2 or whatever hanging out in your build. And then adding a dependency is sort of a big deal. Like people stay away from adding dependencies because like it complicates your build. It might, it means you have to like maintain that dependency, and transitive dependencies may conflict. Like library A depends on some version of library B, and then library C depends on some other version of library B, and you depend on both A and C. And so now you have a dependency conflict that you have to resolve. And this is like a huge issue. I mean, we all know this from Scala. Now in Unison, like dependencies are just hashes. So the dependencies are individual definitions. So you don't actually have dependencies on entire libraries. You just have dependencies on the parts of the libraries that you're actually using, and only on the versions of things that you're actually using. And then different versions have different hashes, and they can coexist even within a single Unison expression. And if you try to pass one version of a data structure off as another, you'll just get an ordinary type error when you try to compile it. And adding dependencies is trivial. You just put it in your code base and you're off to the races. Any questions about this?
Yeah, I have one.
Okay.
So you mentioned here that I could use two different versions of, say, the same library, even within the same expression.
Yes.
So A, in practice, how common is that in the Unison code that you're writing? And B, how do you keep from getting confused?
Well, you'll assign them different names. Like you might have some kind of naming convention where you give the old version some kind of number. The way that I've been working is that I'll have under my project namespace, I'll have a trunk namespace, which is my main line that I'm working on, and then I'll have a releases namespace, and those will have different versions of things. But there's nothing preventing me from importing one of my release namespaces and another namespace in my trunk namespace, for instance, and using objects from both of those namespaces in the same expression. And it's fairly common if you are doing like mediation between the two versions. Like for instance, if you are writing code that upgrades user data that was made with one version of your library, and you want to upgrade it to a version that's with to the new version, right?
So we have a question in chat as well. So as a developer, would I still refer to the function by name and not by hash? So I guess that's an editing question, right?
A what?
Editing versus what's actually stored.
Oh, right. Yes. So yeah, the programmer experience is that you still just refer to the names. You can use a hash qualified name if your name is ambiguous, or if you want to use like a specific version of that name. You can also use just a hash if you want. Like you can use a hash literal if you like want to be really specific. But yeah, normally you just you have a namespace that assigns names to hashes, and you just use those names.
And is that done automatically, or do you actually have to do that at the start of the project?
That's done automatically. I mean, it's done with a combination of manual intervention and automatically. I mean, it's very similar to how Git hashes are automatic, but they're also manual, right?
And Martin Snyder asked whether, he says, this makes it easier to stick with what you originally had. Is there an easy way to upgrade your code to use the latest version of everything if you wanted to try to do so? And of course, you're willing to pay the associated price with that.
Yeah. So the Unison codebase manager has these objects called patches. And so you can actually write a mapping from old hashes to new ones. And you can publish that along with your library if you want. So then you can automatically upgrade people who want to like use the latest version of everything. And so they just have to like run your patch. And coming in a later version, maybe in the beta, patches will be Unison expressions. And so you could edit them in the language itself.
So what are they now? Just like a table?
Yeah, they're just a table from hash to hash. But it would be cool if you could put arbitrary Unison expressions inside of there. So they could be functions from hash to hash. All right, moving on. So perhaps the biggest benefit and kind of like the ultimate purpose of all of this is of deterministic hashes and the structured code base stuff is the fact that we can send code efficiently and unambiguously over a network to a remote location. So then we could write code that describes its own deployment to like a remote location or to a cloud infrastructure. So in a traditional setting, you have a program written in your language that describes what a single OS process is doing. And then deployment of that program will be described out of band by some other tech, like CloudFormation templates or, some Terraform scripts and Kubernetes and I don't know. And then the build deploy cycle is managed by some other tech that you host on a server. All right, so in Unison, the program can describe an entire distributed system, and then to run the program is to deploy it. So there'd be no build, and the deployment is just written in ordinary Unison code. So we'll get into what that is here in a minute. So most distributed systems today, they use either message passing or they use RPC. Well, RPC is sort of falling out of favor, but there's really just sort of these three paradigms. There's RPC, there's message passing, and the event bus, and this means that all of the code either has to be deployed in advance to every location where you want to run it, or the programs on the network have to agree on a protocol or a message format if you want to sort of evolve different services at different rates and things like that. In Unison, since the code base is structured and every Unison object is an unambiguous hash, we can just write programs that distribute themselves to remote locations. So all the nodes in your network are just like running Unison beforehand. And that's the sort of code they have to agree on. But they don't all have to agree on like the version of Unison, but they all have to run Unison. And then the nodes can just communicate hashes. And when necessary, when some node doesn't know the definition of a particular hash, we can simply send the code. And so you can ask any location to execute an arbitrary Unison expression. And this is just an ordinary Unison library. Well, it's not an ordinary Unison library. This is a Unison library that will allow you to do this. We were actually working closely with Heather Miller on this, who's, has been pretty active in the Scala community in the past, and distributed programming guru. And so yeah, we have this API that she and Paul Chisano designed. It's pretty cool. Here is an example of that. This is sort of using an old version of this, but this conveys the idea. So this is a distributed MapReduce that could potentially be running on like 1 million nodes or something. But the thing I want to sort of draw your attention to with this is that it doesn't look all that different from a MapReduce or like a fold map or something that you might be running just on a local machine, right? The only difference is really in this sort of fork expression. And what that fork call, at least sort of conceptually, is doing, it is retrieving a location from some source, like a node pool or something, and then continuing with the evaluation of the expression in parentheses, like after that sort of tick. So the tick means don't evaluate this right now, like save this as an expression and pass it to fork. And then fork will retrieve a node from whatever the sort of current node pool is and send it off to the an available node. So even though what's happening might be very, very complex, the programming interface to distributed systems, it can be very, very simple. And it could be as simple as this. Now, obviously, this is not going to be fast or anything like that. Like, you'd have to do some software engineering to make this nice. But at least conceptually, it's going to be this simple. Questions about this? All right. I will move on to Unison's effect system. So we have this system of abilities, which we're calling abilities. And we got this idea from a language called Frank, which also calls them abilities. But a lot of the literature calls these things algebraic effects. And this is sort of how Unison handles effects in the language. So instead of having side effects, we have effects. So we can remain sort of purely functional in this setting. So you define an ability using this sort of ability block. So you say ability, for instance, here's an ability to fail. Oh, I still have this sort of S here. Well, anyway, ignore that S. Let me actually just get rid of it. All right, that's better. No, it's not. Anyway, we'll have this ability fail, which has a single constructor, which is called fail. And that constructs a value which has this type, which has any type A, but it also has this additional sort of ability to fail, right? So the fail constructor basically causes the program to require the ability to fail. All right. So for example, we can write head on list, so which gives you the first element of the list, but the list might be empty. And so if you take the head of the empty list in the first case, which is where we say the definition of head is some cases, and the case where the list is empty, we fail. So we call this fail thing. And that causes the type of head to have this additional fail constructor or fail effect annotation on it. Okay, and that's this sort of stuff in curly braces is the effect annotation. And we can handle the failure, which I'm calling the ability. I mean, it's the you're providing the ability to fail with the handler. So here you can take any program. So the sort of tick means it receives a computation, so not an evaluated expression, but a computation, which is really just a function that takes no arguments. And so this computation of type A requires the ability to fail. And that's the thing that I'm calling P here. P is the program that could fail. And it's supposed to return an optional A. So that's the same thing as like option in Scala. So it has these two constructors, none and some, just like in Scala. And so what's happening here is that I'm saying handle forcing the program P, so evaluating it right now. And that's what this bang operator does. It's like evaluates that computation right now. So once that's evaluated, we see whether it throws any ability requests. And if it requests the ability to fail, which is the first case, then we return none. And this K thing is called the continuation of the program. So it's the rest of the program. And so since we're failing, we don't call the rest of the program. We just return none. And then in the case where it doesn't fail, it gives us some A, and then we return sum of A. Any questions about this? No, it's kind of tough because I can't like point. Okay. Here's another ability. So this is ability to track some state of type S. So it has these two constructors. So it has the ability to put and get the state. So put takes some value of type S, and requires the ability to store some state, and then get gives us the S, and requires the ability for some state of type S. And for example, we could write a program like an effectful function that pushes and pops, given that the state is a stack. And so like if it's a list. So if we have a state of a list, then we can write this sort of pop function, which we just say like, okay, the stack is whatever's on the state. And then we put dropping 1 from the stack. So everything except the top of the stack. And then we return the top of the stack. But remember that head requires the ability to fail. And so the entire type of pop gains these effect annotations of state, list of A, and fail, right? So it requires the ability to track some state of type list A and the ability to fail. And then push, you cons the A onto whatever's on the state. Like you should call state get, and you add whatever A you pushed onto that. And then you put that list. The thing that's kind of cool here is that even though this is using effects, it's not using monads or anything like that. Like there's no for comprehension or do notation here. It's just straightforward code, and all of the sort of monadicness of it is being taken care of for you. Questions about that? All right. So here's a sort of composite one. Like we can add two things that are on the stack, like the top two elements on the stack. We can add them together and push the result onto the stack just by calling push of pop and push of pop plus pop. So very straightforward, looks like a side effecty invocation, but actually is purely functional. Okay, so to provide the state ability, we have to write this sort of handler, and this thing here it provides the state ability just by sort of interpreting it into a state machine. So this is just sort of like a handler that runs the stack program, giving it some kind of initial state. Now, normally you, like sort of as an ordinary user of Unison, you're going to be using library code that uses handlers. You're not going to necessarily be writing your own handlers like that. Is sort of like an advanced use case, but most people, it's just like kind of in Haskell, you're not necessarily going to be creating your own monads. You're just going to be sort of using other people's libraries. And same in Scala, like you don't necessarily you don't necessarily like author your own data types, like abstract data types. You use like collections, things like that. Okay. So let me just kind of
before you move on, can you back up to the previous slide? We have a question in the chat, and rather than read it aloud, I'll let you do that because you'll interpret it more in the right context.
In the chat.
It's Ashwin's comment. I can read it out if you want.
I gotta like actually drop out of this. Oh, I see. Chat is in like more here. Okay. Should I read this as S has the ability of state? No, you should read this as, so let me go back to the slide. Okay, so this is saying, so run state has a type. So it receives a computation that returns an A, like a value of type A, and a value of type S, and it gives you an A. Okay, so this computation, which is the first argument, which we're calling C, that thing requires the ability to manipulate some state of type S. That's what that means. So that's what the curly brace thing means. So we're receiving a computation which may ask us to manipulate some state of type S. And so what we have to do is to handle that request by handling it or providing the ability, providing that ability. And this run state thing provides that ability simply by giving an initial state of type S and then runs it as a state machine.
And this comes from me, not Ashwin. Can you clarify the meaning of the curly brace syntax versus not having the curly brace syntax?
Right. The curly brace is going to be actually a list of effects. So it's more clear maybe on this slide here. So pop has two effects. It has the state list of A effect, so the stack effect, and it has a failure effect. So pop is going to manipulate some stack, which is sort of the state, and it's going to possibly fail. Right. So this curly brace stuff is just the list of effects that these things may have, and it always comes like either after a tick like that or after an arrow. So you can see that push. It takes an A, and sort of as part of this arrow, it could request to manipulate some state, and it returns a unit, which is what this open close paren means. I can show you some more things, maybe just like in the code base, might be a little clearer. Why don't we just like start up Unison and look at it. Stop share. Okay. So here I have Unison running already. So this is actually my development. So I mean, this is trunk. So this is like not the alpha release of Unison. This is like the current, like the latest version of this. And the reason why is that I'm just like more comfortable with it. Okay, here's this VI. And so, so here I'm in UCM, so the Unison Codebase Manager here on the left. Maybe we should make this bigger. What do you think? Like that? Okay. If I do a list here, ls, I can see that I have two things in this code base. I have the base libraries, which so this is sort of a new code base that I've just kind of like just started. And so I have the base library, which I've imported from GitHub. And I have this other thing, which I imported from GitHub, which is actually a 2048 game, which I'm going to show you later. But we can sort of explore and look around here. Like we can take a look at what's in base. So we can cd base, take a look at what's in my code base. So under this base namespace, I'll have a bunch of stuff. So for example, there's base.list. So I can say ls list, and there's a bunch of functions on list. And we can ask for a definition, like I can say view list.take. Oh, it's built in. That doesn't help. View list.split. There we go. So that's the definition of list.split. Maybe something that's more familiar to people is list.map. So here, list.map has these sort of curly brace things on it. So it takes a function from A to B, which may have some effect E, and it applies that function to every element of the list of type A, and it returns a list of type B, but this whole function list.map may have an effect because the function that we got may also have an effect, right? So this, you'll maybe note that this is both map and also traverse for people familiar with traverse. Like it'll apply this effect and then accumulate the effect just like traverse does in Scala. So map and traverse are actually the same in Unison.
Is there a way to see old versions of this function?
Yes, you can. Let's see, old version of this function. List. So I mean, there is not currently like a command that you can say, give me the previous version of like this definition. But maybe we should add that. But you can like go and you can get the history of the whole namespace. Okay. So I mean, it's pretty long because like I just oh no, actually it's pretty short. It's just really big because I imported the whole base library. But it tells you like this is the hash of the actual namespace. So both your whole code base and also every sub namespace have a unique hash, and you can actually CD into those hashes. And so you can go back in history, just like you can go back in history and Git using the hashes and the commit names.
So speaking of hashes, here's an interesting question from the chat.
Yep.
How is the hash key of a function calculated for a recursive function?
That's a good question. It is actually done by computing the hash of all of the functions together as a unit. And so we call this a cycle. And so we actually just stick all of those definitions, those mutually recursive definitions. I mean, if it's just one function, it's just that function itself. But it actually just becomes a local function within a larger definition, which is called the cycle. And then we hash the cycle, and that becomes the hash. Does that help?
Dan, does that answer your question? If not, pipe in and clarify, please. And feel free to unmute to do so. Okay, I got a yes, thank you on that. Feel free to move on.
Okay, great. All right. Yeah, the thing to note is that it doesn't actually use the hash to recur. It calls a local definition to recur, and only when you enter into it does it use the hash. Okay, where was I? What was I going to show you? Right. So if, we looked at list.map. We can look around and see what's here, and there are like docs for things as well. So like recently I was messing around with the map. So oh, and you can actually use these numbers here. So I say view 3, which gives me the definition of map.adjust. And if I say docs of adjust, it gives me the documentation for that definition. And docs are linked to the value using this sort of system of metadata that we're calling links. So if you say links of adjust, it tells you all of the metadata that's on there, including the author. So there are 3 authors on here. And the copyright holder is data map internal. And yeah, we can actually look at this license here. So if we say view 4, it's a license, And the license is a Unison expression. It's an MIT license. So that's kind of cool. So there's sort of first class support for copyright and licensing in here. And like, if you have a whole library full of stuff, you can like ask, does this use anything that has like GNU in it or whatever, or GPL licensing? And it can tell you definitely no or definitely yes. Yeah, so this documentation here is now rendered sort of out here using UCM, but this is also just a Unison expression. This here, the docs for adjust. So we can actually view adjust.doc. So you can see that this is a Unison expression called adjust.doc. It has type doc, and it has this sort of special syntax. And we're significantly expanding this syntax sort of in the next few weeks. You know, like making examples and things like that has kind of poor economics at the moment, but it's pretty rich and you can do like very cool stuff with it, but it needs some love and attention to be more ergonomic. But you can see that, you know, this is like calling out to list reverse. So this at list reverse here thing here is an expression that actually refers to the hash of list reverse. So if we change the name of list.reverse to something else, then the doc it won't be updated. It won't, like I wanted to say it will be automatically updated, but it actually won't change at all. It will just show the new name of it whenever you render it next. So that's pretty cool. So this doesn't use any like actual code, like Unison code, but there's this thing called signature. So at the top, it shows you the signature, so the type of adjust. And so you can get that in your doc expression. So you can see here is the type of adjust. So what adjust does, it, you know, given a key and a function from value to value, it will transform all the values. I mean, transform the value under that key using that function. Great. I wanted to show you like what the experience is like writing some Unison code. Unless there are questions about docs. All right. I usually get questions about comments, and the way that we're handling comments right now is a little bit janky, but we're looking for a better solution. So, you know, you can do comments like, but it's thrown away. Like it doesn't actually get added to the code base. So that's not great. So what people are coming up with as a solution is just putting a string in the block, and that becomes the comment. So that's kind of cool. But so okay, here I have some Unison code that I wrote previously. So I was just kind of, what I sometimes do is just I look through base and I'm like, okay, well, is there anything missing? Like for instance, nat is the type of natural numbers. So no, there's all kinds of stuff here like Hamming weight and decrement, and there's, you know, addition and multiplication and all kinds of cool stuff, but I don't see greatest common divisor here. So let's add that. So the definition of greatest common divisor is just as follows. You know, it takes x and y, and then I have this sort of recursive function in here. I don't need to make a local function called go, but it's a nice convention, and it also helps the type checker a little bit. So I like to do that. And this is what a recursive function is going to look like in Unison anyway. So the definition of GCD is that it calls go x and y, and go x and y is defined here in line. I mean, just in this block. So if y is 0, then it's just the first argument. Otherwise, it is the greatest common divisor of y and the remainder of dividing x by y. Right? So now I've written this code. What do? I save it. And the Unison codebase manager now comes back and says, okay, I've type checked this thing and it has this type and it's okay to add. And I'm like, great. Okay, so it actually, I gotta be a little bit careful here because it's called nat.gcd and I'm actually already in the nat namespace. So I'm gonna say back. That takes me back to base. And so then now I do add. Okay, I've added nat.gcd. And it's added default metadata for me as well. So if I say links of nat.gcd, you can see that the author is me and the license is copyright Unison Computing 2020. I should update that to 2021. Maybe I should make that happen automatically. Okay. So I've now added greatest common divisor to the code base. And if I want, I can just throw away this source code because I will never need it again. Okay, it's gone. So these, a line that has at least 3 dashes is called a fold, and Unison will ignore everything below the fold. So if I save this file now, it'll say I found nothing. Okay. But nat.gcd still exists. It's in my code base. So I can say view nat.gcd and it's still here. But the source code is gone. But I can always recover the source code by asking Unison what the definition is. Question?
We have a couple questions.
Cool.
One, which you can defer if you want until you're done going through this part, is when would you expect folks to start using Unison for real projects?
That is a good question. I mean, the short answer is not anytime soon. But the longer answer is that we expect that, you know, there will be some people who will want to use Unison for real, perhaps this year. And the aim of the company of Unison Computing is to make the experience for those people completely delightful. So, you know, for people who want to, like, you know, I'm assuming that maybe this is like a couple of people in the beginning, but we want to, you know, make this a really great programming experience in the end. So we're really focusing on that. But, you know, people have made, like, I mean, this 2048 game is like real code, right?
So before you get to that, and before I forget, there's another question, which is any thought to making comments part of the history like the license entry? I think you already touched on that a little bit, right? When you said that comments are kind of janky right now and people are using strings, almost Python style, if you'll pardon the insult, but they're using strings because they're captured because they're expressions. So it sounds like you guys are thinking of coming up with a comment approach that is more an expression or something that can be captured as part of the code base.
Yes, yeah, that's exactly the kind of thing we're thinking of, like some kind of Unison expression that actually annotates the code that can evolve separately, or you know, that you can look at without like looking at the, like, you know, we don't want to make it part of the code because like it'll change the hash, and so it's not great like to use strings, the fact that it changes the hash. And so if you could change a comment, like, do you really want to like upgrade to a new hash? I don't know. It's something that we just really need to think about, but this is just for inline comments, right? But documentation, you know, like the sort of Unison doc, so that's all done with these sort of links.
And one last question, which is mine, and then we'll let you move on. So I noticed that when you viewed nat.gcd, having deleted the code, it looks like, and the code's gone, so I can't compare it, right? But it looks like it used the same variable names, for lack of a better word, right? So now names don't mean anything in Unison,
right?
But it preserved your local names in the code base.
Yes.
Anyway.
Yeah. So I mean, it has to have some names, but the hash doesn't rely on the names. These sort of local names are just sort of annotation on on the AST. The hashing is done after removing all of the names. So if I change some of these local names, okay, if I say, replace X with A, like that, I guess I could have done a substitute, but whatever. Unison will say, I already have this definition, go away.
And if you view it again, you're still going to see the X.
Yes, that's right.
Okay, that makes sense.
Mhm.
Okay, I don't see any other questions in the queue.
All right.
So go ahead. Thanks.
Of course. Okay, so the definition of GCD is now in our code base, and like we're ready to. I could like push it to base right now if I wanted to, but I'm not going to do that. I'm first going to add a test for it. Well, I have least common multiple here. I may as well save it below the fold. Keyboard shortcuts for that kind of thing. Okay, so I have two tests that I've written. And so the way that you do a test in Unison is that, I guess I should do this first. I should tell you about watch expressions. So you can sort of use this as a REPL, which is just in my text editor. If I open a line with greater than, I can just type a Unison expression here, like 2 + 5, and save. And once I save it, UCM will pick that up and evaluate that expression for me and tell me what the result is. If I annotate this as a test, then it will, it'll think this is a test. So if I say expect true, does that work? No, it needs to be a test. Okay. Is it just true? No. Oh, I forgot what the actual type result. So find something of type Boolean to test.result. Check, that's what it's called. So I can search my code base by type. As you can see, like if I say find colon and I give it a type, then it'll tell me all the things that have that type in my code base. So test.internals v1 test.check has this. So all I have to do is say check true. And now I have, wait, what is this? Unknown term. Okay, so I have a bug in my branch, but that's fine. But the thing to note that I want to draw your attention to here is that I didn't have to import anything, right? I just wrote check, and that was totally fine. And the reason why is that we're doing two kinds of disambiguation for you. So I could do like an import statement, which is called use. So I could have done use test.internals, like .v1 dot whatever. So that would be done, like, so this is actually going to be a space. So it takes a kind of a list. So I could say I want check and expect and some other things. So that's like an import statement, but I don't need this. And the reason why is that this suffix is unambiguous. So check, I only have one thing called check in my whole code base. And so this works just fine. And even if I had multiple things that were called check in my code base, it would still be fine because it also does type-directed name resolution. So if there were another thing called check in my code base, which had a type that wasn't Boolean to test results, it would still find it because this is the only thing that type checks. So, it seems like a little thing like ergonomics for programmers, but like not having to manipulate long import lists is tremendously useful, I think. Okay, so to write a test, we just begin the line with test greater than, and then we write our test. So a simplest possible thing is to check whether the Boolean true is true. But a more complicated thing here is like, okay, we want to test that the greatest common divisor is in fact a common divisor. So I call this function called runs. So if we say find runs, it takes a number, a natural number. So It will run that many times, generate that many test cases. And then it takes a generator of tests, or it takes a test which requires this generator ability. And it gives me a test result. And it will sort of pass along whatever this E effect is, which in practice, I mean, in this case is nothing. Okay, so if I call runs 100, it's gonna run this block 100 times with different values. So it's gonna sort of generate 100 test cases. So this is kind of like Scala check or quick check. So I say X is a non-zero nat. And if you say non-zero nat, display 2. All right, that was a slight bug there. I forgot what 2 was. But yeah, so it generates a nat greater than 0. Great. So I want 2 nats greater than 0, calling them X and Y. And so I'm using this sort of bang pattern to force this computation. So the non-zero nat has this type where it like has an effect. And so you can't have like naked effects. You have to like have them captured in this computation. And that's what this tick means. Okay, so I'm saying like, okay, definitely give me a non-zero nat, definitely give me another non-zero nat, and then, check that X, that the GCD divides X and that the GCD divides Y, and say call expect at the end, which takes a Boolean and gives me a test. All right, and so since runs takes a test, we can pass that as the last expression in this block. So a block returns whatever value is at the end of the block, just like in Scala. And so we end up with this test that checks whether the GCD is in fact the greatest common divisor of any 2 numbers is in fact a divisor of those numbers. And then we test that that the greatest common divisor is a multiple of any common divisor. So, using this other test. So this is like a little test that I came up with for GCD. And so now if we save this, it'll say, okay, great. These tests passed 100 test cases. We also note that now this thing is cached, which means it actually didn't run these tests at all because it's run them before. And it remembered that they passed because this whole test expression has a hash, and we just remembered that it passed 100 tests. Okay, so now I can actually add that. Was there a question?
Can you take a quick look at the chat window? Last two comments.
I mean, can I? I don't know. Okay. Okay, is an ability equivalent to a type class? No, but you can use an ability like a type class. An ability is much more similar to like a concrete monad or a data type. It's yeah. I mean, if you're familiar with monads, it's very sort of similar to that. But and yeah, it can definitely be used similar to type classes. But you can't, like, for instance, you can't have like a monad ability, right? That doesn't make sense. Whereas you can have a monad type class. Yes, so type classes are how you implement effects in Scala. Rather, so individual effects in Scala are instances of type classes. Like, for instance, I mean, for example, like a state effect is an example of a monad or an applicative functor or whatever. But applicative itself is not a type class. I mean, is not an effect. Okay, cool. Now that these tests have passed, we can add them to our code base. Great. And added, me as the author and all that cool stuff. And the last thing I want to do is to add a, I want to add some documentation. Doc. And then I open a documentation block. And I want to say like, okay, well, give me the first, start with give me the signature of nat.gcd. And then say, well, nat.gcd. So now here I'm referencing the hash XY. I mean, it's better than nothing, I suppose. And then I can add that to my code base. And now an important step that I need to do, which we're going to automate in some future version, is link this definition to my code. There. So now if I say docs nat.gcd, I get the docs. Awesome. Okay, so now I have a new definition in my base, and I want to sort of like push that to for others to be able to use. So the way that I can do that is actually have, so what we do is we push things to GitHub. So I actually have Unison programming language. Okay, so the base library actually lives here. All right. So the Unison base libraries have been pushed to this repo. So this is the actual code base repo format in here. So if you look at inside what's inside of this this GitHub repo, it's a bunch of binary stuff actually. Like the actual values in here are just directories with names that are hashes, and the contents of the directory are files, which are binaries. So like it's completely not readable by humans, but UCM gives us some tools for manipulating this, and we're replacing this system with something better. Once you go to a non-file-based system, how would something like this work with GitHub? Right, so what does a PR look like? I'm actually gonna make a PR right now. Okay, so this is the base, the official base right here. So now I'm gonna go to I'm calling that my base. Okay, so this is my base. And so it just has this Unison v1 code base directory. And so that's actually on, this is what I'm gonna push to. So I should be able to say, okay, so I have base here, and I should be able to say, go into nat, and that's because I really only care about nat. And now I want to say push to, if I say gh tab, it should give me GitHub. Yeah, github.com/runarorama/mybase, and then special syntax : and then I give it a Unison namespace that I want to push to. So I'm going to call that, I guess I'll call it GCD. Make sense? So I say .gcd because I want to actually push that to the root of my code base. So I guess I could call it something else, like prs.gcd, something like that. It can be called whatever you want. I'm just going to call it GCD. So this will like pull some things down and failed. Oh no. Oh. Okay, github.com, Rúnar Orama, my base not found. Wait, did I just spell that incorrectly? Huh. Maybe. I just upgraded to Big Sur on my Mac, so that may have tanked my Git, actually, my Git installation. Push. I think it might be that. Because it looks the same. Anyway, sorry about that. I think I destroyed my Git installation. I need to like reinstall Xcode. But yeah, so it uses Git under the hood, and what it actually does is that it pushes these definitions to that repository, and then I can then pull it using I can merge it into base and review the PR using this tool.
So while we're waiting, you know, it's pushing the binary compiled version, or what? What is it
Yes.
pushing? Okay.
Yes, it's pushing the binary compiled version.
But then if you do a git diff, it's somehow knowing to use the metadata.
It actually does not use it. It doesn't do a git diff.
Okay.
So all right. So
guess-
it's actually finished. So I can show you what happens. Okay. So now it pushed to this location called GCD, and now I can actually just create a pull request. So if I say pr.create, and I want to create a pull request from github.com/Unison web/base.trunk to my GCD. Oh, it's trunk.base.net. Right? Because that's the namespace I pushed. So now I'm just going to generate this sort of diff, this pull request. And that'll take some time because it's like going through Git. But it's all cached, so maybe it'll go a little faster. Okay. It's saying it's added a bunch of definitions. That can't be right. Trunkbase.net. Oh, I just have the namespace wrong. It's trunk.net. Because base is the root namespace. Okay. So under this repository, there'll be a bunch of namespaces. One of them is called trunk, and the other one is called like releases. And releases have different releases for like different versions of Unison. But trunk is the latest one. I want to push to that, but I in particular want to push to the NAT namespace.
So just to clarify your work here, since that was a review, nothing actually got pushed.
Right. Okay, this looks more like it. So it added these definitions: GCD, GCD.doc, test common divisor, and test multiple of any CD. And then it shows me that like it also added metadata on these things, which is like the documentation, the license, the author, things like that. Cool. So this is what the PR sort of looks like here. And now if I want to sort of like load this, so now I've actually constructed the PR. So then what I would do to like actually make a request of someone to pull this is to just send them this block of text. And what we're doing right now is we're actually just opening GitHub issues on base. So I can just do that right now. Unison web/base. And if I create an issue, I'm showing you how to contribute to base, which you can do today if you want. Well, tomorrow, because it's getting kind of late. So if I say new issue and I say Unison pull request, get started. Great. So just for expediting things, I'm going to say adds GCD, which is and then I can paste my pull requests down here and I say submit new issue. And then whoever's reviewing this pull request will see this. What's happening?
Maybe you need a title.
Oh, I need a title. GCD. Oh. Thank you, Brian. All right. So then whoever's reviewing this pull request, it sees like, oh, okay, great. Here's my pull request. Let me just grab this. So this is a command that I can just put into Unison. So I'm going to say PRs. It's a new namespace. I'm going to call it, GCD maybe. GCD PR. And I'm going to paste. So that should be quick. Okay, so it checked out some stuff and it did some merge and stuff like that. And inside of this namespace is now 4 namespaces. So base is the base before the merge. Head is the thing including the GCD that I just did. Merged is the my changes merged into base. And squashed is the merge with the history squashed, which is usually what you want. So we can actually just say, okay, are there any differences? This is what we expected. Are there any, do we have any conflicts? There's something we need to do. No conflicts in progress. Great, so this is ready to merge. So now I can say push squashed to, what is that actually? Let me just check. Push command, remote. Oh, remote is first.
Didn't it actually show you the command above in the output?
Oh, it did. You're right about that. Oh, yeah, it does. I want the squashed one, so I'll just grab this command. I'm ready. Push. Okay, and now like everybody can, well, once this is done uploading, once Git is done doing its magic, there, now it's done. So now everyone can get the greatest common divisor of 2 natural numbers, like a boss.
So to answer one of the questions in the chat, what's the PR actually look like?
What does the PR actually look like?
If we go look at this in GitHub, normally when you look at a PR, since code is text-based, you'll see a diff, right? And you'll see files affected. You'll see here's what changed. What's a Unison PR actually look like in GitHub?
Oh, it does not have a representation in GitHub at all.
Okay.
Right. So the PR was really just this text. The PR is just this text. And then to load the pull request, all you're doing is you're pulling things from both repos and you're merging one into the other. And so UCM is doing this for you automatically, and it gives you this namespace with the results. And the thing that you can do to sort of review the PR is to look at these results. So for example, you can diff 2 namespaces to see what has changed. You cannot at the moment diff 2 definitions. So that's something that's coming later. But you can edit both definitions and then diff them using text tools.
So as a practical matter, implication of what you're saying, if you push a new version of GCD and I choose to adopt it, and then suddenly my code is not working the way that I wanted to, and there's no current way for me to say, okay, what did Rúnar do to be, what changed between the last version and this version? Maybe I can help him debug it or see
Yeah,
why my
sure.
code is breaking.
Yeah, you can just get both of the definitions. So I can say, give me the squashed GCD, and then, well, imagine there's a base GCD, so where I can just get something else from base dot nat dot, I don't know. Well, I don't know what's in that. Like a lot of that stuff is built in, so I don't know what to get. But you can just like put as many definitions on here as you want, and then if you say edit, oh, I got that wrong. Squashed. Oh, this is already nat because I only pushed the nat namespace. So edit squashed dot GCD. Okay, so it's actually put this in my VI. So if I go to VI and I load, now the GCD is now at the top above the fold, and it introduced a fold to save all whatever other work I was doing down here. So if we had two definitions, you could just put them both in my VI. Like if I had two different definitions and they were slightly different, like let's say I actually introduced this go thing. For instance, like I got rid of the intermediate function. Like these are two different definitions now, and I can just diff. Oh, no range allowed. Diff this. Oh, need to open that on a new buffer. New buff. Come on, split. How do you do a new buffer in VI? I don't remember. New.
Martin's answer is Q bang.
Oh, it's new. I was just overcomplicating things. Okay, so then if I have two different buffers, I can just like diff them. So you can just use your ordinary text tools to like diff definitions that are different. But there's no sort of like, at the moment, we don't have like GitHub built, right? And we actually can't use ordinary GitHub because GitHub is very much geared towards textual representation of code, which we just don't have, so we can't use it. So ultimately, we'll have to build something that's very similar to what GitHub does, like where you can look at like an entire namespace and diff it with another entire namespace, and it'll show you like all the textual differences on a web page. That is still to be built. Does that make sense?
I'm not seeing any questions about it, so I'm going to assume yes.
Okay. This. Where was my other? I actually just. There it is. No. Anyway, I'm not very good at using my VI at the moment. But yeah, the long and the short of it is that right now what we're doing is we're just using our ordinary text tools. Cool. I think that shows you a lot of like what it's like to use Unison at the moment, and sort of like why I've told you why we did this and sort of how it conceptually works. And I mean, I hope that you get some ideas spin in your head. It's it's early days still in the Unison community. Like stuff that if you decide to like help out or come and join us, you could make a huge impact on like the future of this programming language. And also Unison Computing is hiring. So if you are interested in functional programming and you're also a distributed systems ops specialist, then we definitely want to talk to you and try to get in touch with me, please.
So does your 2048 game work?
Yeah. So it's not mine. I mean, somebody else wrote this. I can show that to you.
That'll give
So if
people
you go to-
time. That'll give people time to queue up any more questions.
Sure.
We are coming up toward top of the hour, so
Yeah, that's cool. We can just show you this. So Sam Roberts wrote this. So this is on his GitHub. This is a 2048 game written in Unison. To get it, you just pull from this repo into your code base. So I've pulled it into a namespace called _2048. And to run it, we just execute this. So just go to the root. You can see that I have the 2048 namespace in there. And if I run play 2048 in my, oh, sorry, I need to restart my, this is actually written for an older version of Unison. So I need to start the current version of Unison because the version I was running is like the development version. So it doesn't work. So if I run that, now I'm in 2048. And so yeah, it works. So you can play 2048. Pretty great. I think it's just awesome that somebody did this. How do you quit? Control C, I guess. Yeah.
So it looks like, given your use of stack earlier, is Unison currently written in Haskell?
Yes.
So I guess you'll have crossed the Rubicon when you re-implement Unison in itself.
Yes. So we have several sort of steps along that route. The first step is to implement the code base in Unison, or to add a code base management API to Unison so that you can manipulate your code base using Unison. And then filling that out with functionality so that you can actually compile Unison in Unison. But like just being able to like manipulate code base using Unison expressions, that would be huge.
Okay, so do we have any final questions for Rúnar? I didn't realize we were actually going to run right up to almost 10 o'clock, which is awesome.
Sorry, it was kind of slow.
No. We allocated the time. I told you in a DM you could use all of it if you wanted. Do we have any more questions before we wrap it up for the night?
I don't know how much of this you want to or have the time to get into, but I'm curious how the distributed earlier in the presentation you described how Unison has a different deployment model, and can you discuss how that works or how it's envisioned to work?
Yeah, I'm not sure what like level of detail we can go into, but sort of at a high level, I mean, it's the way it works is that you just have a Unison library, and you call Unison functions, and what those functions do is that they take Unison expressions as first-class objects, and they also take we're called just logical locations, which are then backed by the actual implementation of it is going to be, essentially a socket that's talking to a Unison node. And then you send an expression to the socket and it executes on the other side. That's basically how it's going to work. I just want to also point you to the Unison website. So at unisonweb.org, like you can read a lot more about Unison. you can read there's lots of documentation. Like there's a whole language reference, like the specification of the actual language itself. We invite you to join the Unison Slack. It's pretty active, and we're very friendly, and we like to use our real names, and so it's not like anonymous trolls and things like that on there. And this is the Slack here, and like somebody made this like canvas thing, like they're making drawings or animations in Unison. Like people are doing cool stuff with Unison at the moment, so it's awesome to see. Somebody wrote a web server as well. So pretty awesome. But yeah, unisonweb.org if you want to check out more about this.
Okay, and if that's all we have, I would suggest everybody open up their mics and applaud, but I'm not sure Zoom would be able to handle that. So I would just like to say, I mean, we could try it if you want, but I'd like to say thanks to Rúnar for letting me strong arm him into this, to giving this presentation in the first place.
Twisted my arm.
Yep. And I was able to do so remotely, which was kind of a surprise to me. And thanks to everybody for joining. Sorry again that it took so long to reboot the group, but this is a great kickoff presentation, I think, for rebooting the phase user group. So once again, thanks, Rúnar. I learned something. I hope everybody else did as well.
Thank you, everybody. Have a lovely evening.
Thank you, Brian.
Thanks, Brian and Rúnar.
Thank you.
Thanks, everyone. Have a good night.
Thanks.
Thanks again, Rúnar.
Thanks.